And is doing scientific research in homological algebra. And this is a very abstract field of pure mathematics, and I want to show you, give you an idea of the domain, which this is the hard part, and how can we use Smalltalk to work on this domain. So, mathematics is about abstractions, similar to Smalltalk or in general modeling anything. So let's start with a very simple example that everybody understands, which is some function. And think of a very smooth function, any kind of it, and consider a point x0 in the x-axis, and then we will project this and find the value of that point. And one interesting thing that mathematicians do, and everybody is aware of that, is to consider the tangent line on that point, if that happened to exist, right? And the slope of this line is the derivative in that point, okay? This is a very well-known concept. So from this observation that you can actually compute the slope of the tangent line, you can do many things and actually build many fields in mathematics that have to do with tangent planes or hyperplanes in any dimensions, and generalize this dramatically, okay? So basically you are going to the field of geometry. It's not geometry, but many geometries, like differential geometry, for instance. Now, there are many abstractions. This is not the only way to consider this. Another abstraction is to think of some properties of the derivative. The derivative, which mathematicians symbolize with prime notation, is another function, but has an algebraic, is linear. The derivative of a sum of two functions is the sum of the derivative, and if you multiply by a scalar number, is the same happens. It's the same to first multiply and then take the derivative or the other way around. There is a second property that is the product property. So if I take the derivative of the product, is the derivative of the first times the second plus the derivative, the first times the derivative of the second. A very well-known formula, okay? But what's interesting here is that these two things are algebraic. The only thing I'm doing is representing or abstracting or focusing on algebraic properties of the derivative. We are summing, multiplying by scalars, and multiplying together functions, and applying the derivative operator to find something. So, following this direction, we go to another direction. It's not the geometry part of the problem, it's the algebraic pathway, okay? So, we are going to, in homological algebra and in pure mathematics in general, mathematicians take radical abstractions, really radical abstractions. So they start, for instance, from a notion of derivative, which is this, then forget that initial notion and concentrate on the algebraic properties that I just described. So what kind of elements are in this domain, this algebraic domain? Well, we have some coefficients, numbers, okay? But let's abstract that too. Numbers can be anything. You can think of all the numbers you already know, like complex number, real numbers, rational numbers, but there are many others, okay? Let's use symbols for them, and let's say that the coefficients belong to some algebraic structure, actually a ring with name K. There are some main elements that when I started with this were the functions. Now we have a radical abstraction. We have other objects that we will name f, g, whatever, and they belong to a different set which has algebraic structure. We will name this A. This is an algebra. An algebra is a set of things that I can sum or multiply. It's just that. So K and I are similar. In K, I have the coefficient. They are not the main elements. The main elements, the really interesting elements which are rich in nature, are in A. And then we have the derivative operator, which is any operator that operates on these elements and has the derivative property of the product. Okay? The derivative of one function times another is the derivative of the first times the other plus the first times the derivative of the second. So we forget everything, make a radical abstraction, and only focus on the main objects and the main operation here, which has, I don't know now what the D is anything that has that property, with that property, anything, okay? For instance, the usual derivative. So, now we want to model, think that we want to model this in the computer, in Smalltalk, okay? So then we need a model, a formal model for this. Mathematicians also create formal models. With formal models you can think of just letters, characters, formal. It's a syntactic construction where I put some rules. So they create, they introduce some definitions. For instance, the tensor product. Which is the tensor product? It's the abstraction of the usual product. But this syntactic thing is, if you think in fractions, for instance, if you have number 2 and number 3, and you want to divide 2 by 3, you cannot do that. So mathematicians, before the rational number existed, say, okay, I cannot divide 2 by 3, but then I will write 2 line 3. So I create a syntactic solution with text, and these are the fractions, okay? This is similar but with the product. So we create a copy of A, and now we have A and A in the same way that with fraction we have the integers in the numerator, and again the integers in the denominator. Integers are pairs, okay? These are pairs too. Another definition is that we want this product to have some nice properties, algebraic properties. So the first thing is that I can multiply a tensor with an element coming from the left, and I will multiply that by just putting this element into the first component of the product tensor. Similar again to the fraction. When I multiply by a number, I put the number on the numerator. But for the right multiplication, which will be equivalent in the example of fractions to multiply the denominator, I am trying to multiply on the right here. Then I will, because I have the derivative in mind, I have this rather complicated formula, which is not just only G acting on from the right, but also with an additional term, which is minus the tensor product of F and G. You may think why this is complicated. Think of the way we sum fractions. 2/3 plus 1/5. It's not that simple, the solution, okay? So for some good reasons, the good definition is this one. And with these definitions, I introduce the derivative of f in a totally symbolic way. The derivative of f is now a very abstract derivative operator, is now just to put f on the right or on the product tensor with 1 in the left. So we have to check whether this derivative operator has the derivative, the property of the derivative. But this is very easy, because from the first equation, if we replace one tensor f with the derivative of f, we will get on the left the derivative of f times g. Right? So this is what is on the left side. On the right, we have one tensor fg, which is the derivative of fg, because the derivative of anything is one tensor that anything. And on the right, on the end, I have this f tensor g, which is f derivative of g. So if you pay attention, this is exactly, you have to send the minus term to the other side. This is exactly the derivative rule. So with this formal model, made up of letters and symbols, we have a derivative operator that behaves as the usual derivative. So this is the basic construction that we have in homological algebra. So I want to give you an idea of the homological algebra domain. In the homological algebra domain, people start making compositions. So far we saw this f tensor g thing, okay, which is one tensor, one element. The set of all these elements is a tensor A, okay? So this is a set full of all these expressions. So then you start making compositions. You tensor again, okay? So this start getting complicated. And even more compositions. For instance, this one. So you tensor this thing several times, and know that already omega was a complicated tensor product, and then you add more terms to the tensor product, and then you already consider sums of this, so you start creating crazy things out of the formal model, okay? You have to think that this is not an element, this is a set with an interesting algebraic structure which elements are the tensors complicated this way, okay? So it's the numbers, the indexes indicate the configuration. For instance, omega 2 is because I have two copies of A, and so omega 3 would add to the first original A 3 copies, and omega 4 would add 4, etc. In the case of X, is from, if I forget the first component, which is omega 2, I have 3 on the right, so I have 1 omega 2 and 2 A's in every part. So this is all the possibilities to put 1 omega and 2 A's. So in the first one, I have 1 omega and 2 A's. Then I have 1 A, 1 omega and 1 A, and then I have AA omega. If we add values to the indexes, we will have several omegas and several copies of A, and you have to consider all possibilities and sum them all, and you will get a totally crazy structure, which is a set of things that were very complicated to begin with. So this is the kind of constructions that algebraic homological algebra proposes. Sure.
A more term with A by omega 2 by omega 2.
Yes, but this is just an example of one construction. It's not very important that you pay attention to the details. I just wanted to show you that there are some simple rules of how you build this. This is important for us programmers because I have to understand how to build valid objects out of the ones that I already have, to compose them and create more complicated things as the domain requires. Then there's another notation, because things in omega are already tensors, but for some good reasons they don't want to be confused with the other tensor products. So we use the derivative operator instead of the tensor operator when we take elements of omega 2, for instance. So it is not only about creating composition of crazy structures. It's also mathematics. It's also about arrows, which are mappings, functions. Okay, so mathematicians are not happy enough with just all these structures. They also want to consider arrows from one structure to another, and they think of arrows that have transform things but behave nicely with algebraic properties. So they take sums into sums and products into products. Okay. So this one is called the boundary, because all of this has geometric meanings. And it's very hard to understand the geometric meanings by reading the formula. But this has to do when you have, for instance, imagine you want to represent the illusion of a 3D surface on the computer. Then the usual technique is to build triangles to approximate this shape with simple things, with triangles, okay? So the border of the triangles has to do with this kind of constructions. So if you have something that is a triangular shape, and you go around the border, then you get something that is closed. Because you start in some point, you go along the border all the way around, and you come back to the starting point. So the second shape is closed, so it has no border. Okay, so this function represents that construction, and if you take the boundary of the boundary, you get 0. So this is again a function taken over an element of the crazy construction we saw before, which was x14, and this is mapping to x13. The number decreases because the dimension, when I take border, decreases. I go from dimension 2, for instance, to dimension 1, which is the border of the triangle or whatever. And this is again has simple rules for implementing or modeling the computer, because if I have 4 things, then I have to produce 3. And how I do that? Well, I combine the first with the second, then the second with the third, then the third with the fourth, and then go around the boundary. I come back to the beginning and combine the last with the first. And okay, and the signs change just to add some complexity. So what the mathematicians do with this? They have 2 kinds of things. They have these totally crazy composed algebraic structures, the sets of individual tensors, and they produce many of these, and they produce arrows, which are the mappings or functions. So they put in diagrams like this one. So they create several of these things, and when a diagram is in this case is a square, has a set here, a set here, a set here, and a set here, and arrows. So this creates like a network where you can go from, for instance, omega 5 to first horizontally to x05, then down to x04, and or coming from this way. Doing this is composing the function. I first apply the first function and then the second, following this pathway, and then I go through the other pathway. So this is a notion of commutative diagrams. So this is the way I would compose, or this is the other way. I want to make sure that the two things are the same. These are the theorems of the theory. Every time you have an interesting diagram with this property, is a theorem you have to prove by replacing the definitions of everything and making the calculations. Okay? Now we have a complete view of the main elements of the domain. We have the tensors, we have the sets that create these tensors, and we composed it by tensoring even more. Then we have the arrows, and then we put the arrows in a square and consider commutative diagrams. Now these are the building blocks. Now is where the interesting things start. Interesting things start by creating even more complex diagrams, not just a square, but many in different places with different shapes that create different pathways by composition of the function. So you can go this way or that way or many other ways, and the theorems are to find these constructions that where the pathway doesn't matter because all of them is the same. Okay? And so this is a research problem, the real research problem that these two mathematicians are working on. This is the kind of diagram they want to solve. This is, I will explain a little bit this diagram. The first shape you can recognize is the square, okay? So there are many squares. Now, things are actually infinite. So they have squares on every direction. Not all of them, but most directions are infinite. And there are actually 3 planes. So this is a 3D diagram. So you can live in the first plane, you can live in the second or in the third one. And there are arrows that cross from one plane to the other, and all the crazy compositions and pathways you can think of, all of these commute. Okay? This is, and from this diagram captures very important properties that have geometrical meaning. And this is the magic of all of this. So let's see something. For instance, this one is x14, which comes from the previous slides. And one that is below is x13, which was the other example I gave before. And the arrow B here is the arrow with the combination that took 4 things and produced 3. So this is just an example. There are many other crazy functions here doing this kind of stuff. So how can we model this in Smalltalk or in anything? So I want to have an elegant computations. And so this is Albert Einstein, who happened to work on tensor analysis for doing his research in physics. So he had to deal with tensor analysis. Not these, because these are more modern, more abstract, but the same kind of things with an old notation. But he was not a mathematician, so he went to the books and read and tried to study and didn't get quite the idea. So he got lost. So asked his friend Levi Civita, which was a mathematician, for help with the tensor analysis thing. And there are several letters where they interchange questions and answers or things to review. And in one letter, this is what Einstein said. Basically, is saying, I admire elegant computations, the elegant computations you can make. So I saw this, and my reaction was, okay, I cannot be as smart as Einstein, but at least I will try to be as elegant as Levi Civita. So I wanted to start, now that we understand the problem, we got to start with modeling with some things. So to model this, we had to go from abstract to concrete. So let's take some example rich enough and start building things in Smalltalk. So I said, oh, okay, coefficients are integer numbers. I don't care. This is just an example. And for the elements, F, G, I don't want to model functions or anything. So I model just variables, free variables, which are letters, okay? Free variables. And these, but as many as needed. So an infinite array of variables. So this, if you start multiplying and adding these things, you get polynomials, okay? Like x1 squared times x3 plus 1, whatever. Now, these things, because it's a requirement of the research problem, should not commute. So we will not assume that x1 times x2 is the same that multiplying the other way around, to keep the enough generality. Okay? So these polynomials are actually non-commutative, but this is a detail, which makes the Smalltalk code easier. So I also modeled the tensor products and the tensor structures, and also the arrows, which are not only boundaries. I only showed you boundaries, but there are other things that are homotopies and augmentations and morphisms and perturbations. Note here that tensors have, the word tensor has from tension. This comes from physical things. And boundaries, homotopies, augmentations, perturbations, all of them are terms that have a geometrical meaning, okay? All of these, except tensors, are arrows, are mappings, functions, okay? Complicated things, but all of them have a geometrical interpretation. So I wanted to reproduce these commutative diagrams, so I implemented the elements, I implemented the sets, and I implemented the arrows as Smalltalk messages. Okay? Then I wanted to check whether my model in Smalltalk, then I will show you the Smalltalk code, but was elegant or not. So this is the example of one very simple commutative diagram. So here is the Smalltalk code. I create a new algebra. The free prefix is because the variables are free, just anything. So I create several variables, in this case 6 of them, x1 to x6, etc. Then I create a typical element of the set omega 5, because I want to start going right and down and down and right to check whether this commutes or not. So I created one element. So this is x1 times x2 derivative times x3. So I'm building, omega is a tensor thing. And this is the way you create this in Smalltalk with the model we built. And then, now that you have an element in the upper left corner of the diagram, you can apply the functions. So first, I send the boundary message, which is the equivalent to evaluating the boundary function in the element. Then I take another function, which is the psi function, and then I go the other way around. Okay? Actually, this diagram has a mistake because I don't have psi there, but I know, yes, I have. The boundary is delta. And psi 0 is psi with the argument 0. Okay? So, if you look at this, you will recognize that the notation on the left is the mathematical equivalent to the assertion on the right in Smalltalk. But there is so it's very easy for mathematicians to understand that both things are the same, especially because when they read that, they read this way. They write using Greek letters, but when they read, they use names. They don't say delta, they say boundary. Okay? So this is very expressive, and the code is elegant, and I can write a test to check that the theorem holds, at least in several examples. So what about expressiveness? Because this has a lot to do with elegance. So this is another kind of theorem with involving the things and objects and arrows. So here, I'm composing C with phi, then the identity. I'm subtracting these two functions, and on the right, I'm making a different composition. And I want to check that both things are the same. Sorry, this is different, and this because I'm not checking here a commutative diagram, but other kind of property. But it's similar because on the right I have epsilon delta and delta epsilon, which is the familiar kind of construction that I get when I want to show that a diagram commutes. But here I'm not trying to show that epsilon and delta commute, but if I sum them, I get something that can be obtained with a different expression. In mathematical terms, you can translate that diagram in this formula below, because in the first place, I'm first applying phi and then psi1, then I'm subtracting the identity, and then it is equal to first epsilon and then delta plus first delta and then epsilon, which in mathematics you have to write in the other way around. And if you express the same property in Smalltalk, well, you get this, which is exactly as mathematicians read the previous equation. And also, if you don't read aloud, but you just check, it's very easy with just some few practice for a domain expert to understand that both things are the same. So my thought was this is expressive enough, and so we started to build many tests for different theorems and to check things and to check crazy diagrams and commutative things and to try examples that were impossible to do by hand because of the complexity. I will show you some few examples then, but first, remember that we started this construction in Smalltalk with some very simple example, integer numbers and free variables. But actually, mathematicians are not thinking in these examples. They are thinking in general, totally crazy general examples. For instance, instead of variables, they could have square matrices. You can multiply and add matrices, or functions, or many kind of things. And so there was this need to check whether this particular case was general enough for more abstract things. So once we build the concrete models of all these main building block objects of the theory, we said, okay, we have these free variables, but actually theorems are about general abstract elements or algebras. And what if we specialize the formulas we get using free variables, replacing the free variables with the elements of the theory, the actual elements, which are unknown to the Smalltalk model. But in this, like, for instance, this is a very simple theorem, not from this theory, but if you have x1 plus 1 squared, this is the same as x1 squared plus 2 times x1 plus 1, okay? This is a theorem. So if I prove this theorem for a free variable, then I can specialize the variable and get the same theorem for any element. Okay? So if the equations we get with free variables hold, then by replacing this formula that's called for any free variables, we will get the same equations for any particular variables, but or values. But these particular things can be anything, so the generalization is trivial from the mathematical point of view. So this very concrete example was general enough as to provide insights into the most general and crazy theory just using a computer. Okay, so the lesson here is the algebraic formulas that are proven to be true for free variables, this is what we modeled in Smalltalk, are true for arbitrary elements. This is a mathematical theorem, but it's very intuitive. So,
and what happens if you want to generalize the numbers?
Nothing, because if you have, for instance, a complex number times a matrix, then you create a variable for all these elements. So this is x1. Yes, integers is enough, because you can incorporate the coefficients to the element. So don't think of f, but of lambda f. Good questions. Let me show you how this looks in Smalltalk. Well, let's take any test. I don't know. We have many tests. Let's insert a halt here. Let's run the test. No. Let's run the test with a halt so we can see something. So here I'm created a tensor. Here is a tensor on the right. Okay? Then I start applying these crazy mappings. For instance, in this case I have a contracting homotopy, a crazy mapping. So I have a theorem here. If I apply first the contract homotopy mapping and then the boundary, and I sum these to boundary contracting homotopy, which is the other way around, I get back the tensor I started with. This is the theorem. This is true. So if I evaluate this is true. But the interesting thing here is take a look at the objects we built. So this is the result of applying the first thing. So with a nice print on, a mathematician using just the browser, the debugger or the inspector, get the formula. Okay? And the formula is exactly the same that they write in LaTeX, for instance. And if you go further and compute the boundary of that, then you get even more complicated things, like this one. Okay? And if you then do this, which is the summation of both expressions, you should get the original tensor, which is, that's the case. Okay? And then, for instance, I told you that if you apply the boundary twice, then you get 0. So here we have the boundary of something. And now I'm going to compute the boundary of this. Okay? What I get is 0. This is the main property, which the boundary of the boundary is nothing. Okay? So by manipulating these kind of expressions and objects, and with all the expressivity of Smalltalk, we could build many tests, and we are checking a research paper that is 5 years old, because they could not finish the work because it got so complicated that now requires the help of a computer. So now there is a very good hope very good reasons to have hope to finish the work and to try examples and to make some new hypotheses or thesis.
Is this test checking a particular example, or
this is testing a particular example, which is very general because the variables are free, are anything. But it's a particular example. So what we are doing is we check several. We are not proving theorems. We are checking that the theorems don't have counterexamples. Okay?
These A1 to A8 are the three variables, are models of three
Exactly, exactly. Which here, these are x1, x2. So, okay. So I wanted, my objective here, what turned out from this project is that actually we created, without creating any GUI, we created a model of the thing that is very expressive and is very productive. Expressions can get very complicated, but this is secondary because we never deal with the complexity. We take something and send a message and apply the functions and check that the diagrams are commutative. So we are checking the theorems. But I wanted to prove somehow that this implementation was elegant. So I thought that some metrics could help. So the number of classes here is 40. Think of the general problem, this 3D infinite crazy thing. 40 classes. This number of methods. This is an interesting metric. The ST is the size of the LaTeX source code of the full paper. Sorry, the tech one. And ST is the sources of the smalltalk thing. So it's 32% bigger. So it's proportional. The source code of the implementation of the paper is totally proportional to the paper itself. So we are not saying we solved this incredible complicated problem because we are brave. It's with simplicity, with proportional to the complexity of the original problem. We have several unit tests. These are the number of methods, but every method tries many examples. Okay, so before you asked me, the coverage is 82%, and most of the things that are not covered are the printons, which you don't need tests for them because we are all the time inspecting things. And this is the average of lines of code by method. So this is a very good measure of simplicity. Every method has 3.5 in average lines of code.
What do you mean by line of code? Collaboration or? Sorry? What do you mean by line of code?
Lines of code. Every method. Well, you get the sources and count just the number of the text, the source. Yes.
Uniformly formatted.
Sorry?
Uniformly formatted.
Yes, I use automatic formatting, so the formatting is... but the formatting doesn't matter to get an idea that 3.5 lines of code is not that complicated. Okay? The arity is the average number of arguments. I call it that way. So most of the methods are unary methods. Take no arguments, and some few have one. I don't know. There are some that have two, but in average, it's less than one arguments by method. Subwords. Subwords is the number of words in a selector, not the number of keywords, the number of words. For instance, boundary is one word. Diagonal boundary is two words, but it's still a unary message. And the number of subwords, the average is 1.7. So most of the selectors has between 1 and 2 words. And I'm using the words of the domain. Number of instance variables, slot by class in average, 2.7, less than 3 instance variables every class. Think of the complexity of this thing, 3 instance variables or less. Incursion, 1.5. Incursion is a metric that when you send a message, you get a result, and then you send another message to the result, and then another one. This is incursion. How much, when you write a method, you have to know about all the intermediate answers. Okay? well, a high incursion is not very good because you have to assume a lot when you write. So 1.5 is a good. Polymorphism is the number of times every selector is repeated in all the project. So we have an average of 2.3 implementers for every selector. So the terms repeat. Of course, there are some selectors that repeat many times, like boundary, for instance. And complexity is a measure of how many messages you send in every method. So this is the average is about 5.5 messages in every method. In every method.
That's more interesting.
Yes, it's similar to the number of one or two. And if you take the incursion, which gives you the composition, is almost the lines of code one by the incursion is almost the same. So with this bunch of metrics, I think at least I'm convinced, by using the tool too, that this is a good way to show that the computations are elegant. I might not be so elegant as Levi-Civita, but I tried. Well, I think it is solved. Thank you. Any questions? If someone has some really hard question on mathematics, here is the mathematician. You can ask him. Otherwise, are you happy with the implementation? Yes, yes.
Mathematicians is enough to operate with small directly, or you find that a better interface.
He cannot sit on the computer and start coding and trying examples. We sit together, but I drive the computer, but he is very aware of everything, and he checks and tells me when something is this way or that other. The way we work is like this. He explains me the theorem, the theory. So I say, oh, stop, I have enough information. So I start thinking how to model that. So I start building some things, and I start showing him. I go with him, watching over my shoulder, and I tell him how I am modeling what he wrote on paper. So we check the notation. For instance, an interesting thing is that mathematicians use many letters, Greek letters, any kind of letters, and but they don't name things. So they have this diagram. What's the name of the diagram? I don't know. It's this diagram. But when you program, you have to name everything. So here it comes this exercise of finding names, which is interesting. Yes. And
when the mathematician will write a paper, he will name that name. So that's an application of the exercise. And the name to use it.
Yes. It's productive because the surprising part was that I tried to make you experience the same I experienced in a longer period, which was, I will tell you something. This is a derivative. I am a mathematician, so not all of this is new to me, but this is a specialty of field. So, this is and this is a tensor product, yes, right, and we are composing this, okay, and the description of the domain get more and more complicated, so sometimes I had to say, how I'm going to model this, I had no clue, but thinking and talking and trying, the results were incredibly simple. So it was incredible. At some point, it became very stable. So it became, today it's very, very easy to add more concepts. So he said, I have another diamond. Okay, come on, tell me the diamond. So he starts, it's longer the time he takes to review what he has to tell me that the time I had to spend actually codifying that. So the environment is very productive. We don't have bugs or errors that we cannot solve in a minute or seconds. We have many tests, and understanding what went wrong when some tests fail, for instance, or some error happens, is must be this. Try some example or try some, and the inspector shows us the equations, and it's very easy. So the environment is very productive, very productive. So it's a perfect fit between mathematics and Smalltalk. And in this field, we are not aware of any other pair of crazy people using computers for this field, because computers are used in many fields in mathematics that in this special kind of problems, no, this is something that we are doing for the first time, I guess.
So before this, you used to do all those translations functions by hand. So what we just saw in the inspector was usually written on the page.
Yes, the difference is that they reach some limit, and we surpass that limit. Over 5 years of hard computations by hand, they could not surpass some limit of complexity, and now this is surpassed by far. But even more, if you do some very complicated example with a very big piece of paper, enough ink, and you fill of this paper with formulas, then you put a lot of understanding there and knowledge that you will eventually lose, because it's paper, it's lost forever. But if you model in Smalltalk, you are capturing that knowledge in a very precise way. So this is not just to compute something. We are capturing knowledge. Every time we Smalltalkers model any domain, we are capturing knowledge in our models. And capturing knowledge is a way to create knowledge. Because when you have everything in one place, with a consistent notation, with a scientific notation, which is Smalltalk, because it runs. It's not like the papers that may have errors that nobody will discover until it's probably too late, or I don't know. But there are many in magazines with theorems that are not true, but have very good demonstrated proofs. So with a computer, so the problem is that in computer science, we have tests and we don't have theorems. The problem with mathematicians is they have theorems, they don't have tests. Okay, let's go to dinner.